Now one more example. Calculate voltage gain AV equal to V naught upon VI, HIE equal to 1 kilo ohm, HFE equal to 50. Again, a common emitter amplifier with bypassed RE is given in the figure. We know that this voltage Vi is the voltage between base terminal and emitter terminal, and this is the output voltage V naught. Now in this circuit, the load resistance RL dash is the parallel combination of RC and RL. If RL is not given, we will say the load resistance RL dash will be equal to RC. Now to calculate this voltage gain AV equal to V naught upon VI, we use this formula AI into RL dash upon RI. Current gain AI is equal to minus HFE and it will be minus 50. Input resistance Ri between these two terminals, Ri, it will be HIE equal to 1 kilo ohm, and now the voltage gain AV equal to V naught upon VI will be minus 50 upon 1 kilo ohm into RL dash equal to RC, and it is given as 2 kilo ohms equal to minus 100. So this is the voltage gain of this amplifier. Now if in this example it was asked to calculate voltage gain AV equal to V naught upon Vs, then the calculation would be different. Now we'll see how to calculate this voltage gain AV equal to V naught upon Vs. Now if you want to calculate this voltage gain AVS equal to V naught upon Vs, then the calculation would be different. We have already calculated this voltage gain AV equal to V naught upon Vi. Based on this calculation, we will calculate this AVS. Now the transistor circuit given in the problem can be replaced by this circuit. We have replaced this transistor with this input resistance Ri, and the voltage across this will be equal to Vi. This is the resistance Rb, this is the resistance Rs, and this is the source resistance Vs. Now from these two terminals we can see resistance Ri dash, which will be parallel combination of Rb and Ri. Same voltage Vi will be across this resistance also, because these two branches are in parallel. So now we can replace this circuit as Rs dash, sorry, it will be Ri dash, and across this the voltage will be equal to Vi. Now here we can write From this network we can write Vi equal to Vs into Ri dash upon Ri dash plus Rs. Total voltage gain AVS was V naught upon Vs, and this can be written as V naught upon Vi into Vi upon Vs. Now this V naught upon Vi we have already calculated it. It is AV, and Vi upon Vs can be written from this using this equation. Vi upon Vs is equal to Ri dash upon Ri dash plus Rs. So this is the total voltage gain AVS. If the this AVS equal to V naught upon Vs is asked to calculate. Now if source resistance Rs is 0, if not given in the problem, in this case AVS will be equal to AV into Ri dash upon Ri dash plus 0 will be equal to AV. So if source resistance is not used in the problem, AVS and AV both will be the same. Draw hybrid model of approximate model of common emitter amplifier with unbypassed RE. Now in this amplifier, common emitter amplifier, this time RE resistance is unbypassed. When RE resistance is unbypassed, during AC analysis we have to consider the negative feedback that is provided due to RE. The formulas are little bit changed due to this emitter resistance RE in the circuit. The hybrid model, approximate hybrid model will be like this. This will be the base terminal, this will be the collector terminal, and between emitter and ground this time there will be a resistance Re. And now the other components will be connected like this: RB, no DC sources in AC analysis, Vs, and on the output side there will be two resistances RC and RL, and here we will see the output voltage V0. Again these two resistances in parallel will form a load resistance RL dash. Now again we will define the four parameters which we have seen already. First one is current gain AI. Current gain AI minus I naught upon IB. Again this will be remain same, that is minus HFE. There is no difference. Number two, the input impedance Ri is changed between these two terminal. Input impedance Ri, earlier we have seen the formula equal to HIE, and in this model this formula becomes HIE plus 1 plus HFE into Re. According to this formula, this term is added in HIE to calculate the input impedance. So we can say that with unbypassed RE, input resistance of common emitter amplifier increases. Now we have third term voltage gain AV equal to V naught upon VI. VI will be the voltage between these two terminals and output voltage at the output terminal. This voltage V naught upon VI is equal to AI into RL dash upon RI. We know that Ri is increased just now with this factor. If Ri increases, then AV decreases. So we can say that the voltage gain of amplifier decreases with unbypassed Re. If Re is bypassed, the voltage gain will be high, and if Re is unbypassed, the voltage gain will be low. Fourth parameter, voltage gain, as it was in the earlier case, this time will be considered as infinite. Now the formulas are changed a little bit, and the remaining part will be as it is as we have seen in the earlier case. Now the formula for voltage gain AV equal to V naught upon VI. We have seen this formula as AI into RL dash upon RI. We know the equation of AI minus HFE. RL dash is the parallel combination of RC and RL. RI is equal to HIE plus 1 plus HFE into RE. If RE, suppose RE equal to 1 kilo ohm, HFE equal to 50, then this whole term becomes 51 kilo ohms. While typical value of HI is 1 kilo ohm, so we can say that this term is very greater than HIE. So if 1 plus HFE into RE is very greater than HIE, then neglecting this part, we can write AV equal to minus HFE into RL dash upon 1 plus HFE into RE. Now HFE is very much greater than 1, so 1 sorry HFE is very greater than 1, so we can write this equation as minus HFE into RL dash upon HFE into RE. This HFE will be cancelled out, and the voltage gain comes out to be minus RL dash upon RE equal to minus RC in parallel with RL upon RE. So we can write the voltage gain equation directly from the diagram if it is a common emitter amplifier with unbypassed RE. Calculate V no, AV equal to V naught upon Vs and Ri dash shown in the circuit. HIE equal to 2K, HFE equal to 75. Now circuit given in the problem is now from the circuit it is clearly seen that it is a common emitter amplifier with unbypassed RE. Bypass capacitor is not used, unbypassed RE. In this unbypassed RE amplifier, this voltage is Vi and this voltage is V0. The relation between Vi and V0 we already know. For unbypassed RE, the voltage gain AV equal to V0 upon Vi, not V0 upon Vs. V0 upon Vi is equal to minus RC in parallel with RL upon RE. It is minus of 3K in parallel with 3K divided by 1K equal to 1.5. So this is the voltage gain V0 upon Vi equal to 1.5 volt with negative sign, minus 1.5 volt. Now in this problem we are asked to calculate AV equal to V0 upon Vs. For this will require this input resistance Ri. This input resistance Ri, this Ri dash which is given in the problem is this resistance. This Ri, just now we have seen the equation HIE plus 1 plus HFE into Re will be 2K plus 1 plus 75 into 1K. It is 78 kilo ohms, and the resistance Ri dash is equal to 78 kilo ohms in parallel with 100 kilo ohms equal to 43.82 kilo ohms. Now we are asked to calculate AV equal to V0 upon Vs. We have calculated V0 upon Vi, this voltage gain, and it was 1.5 minus 1.5. Now the circuit shown is Rs equal to 2K. This is Vs, and Ri dash just now we have calculated it as 43.82 kilo ohms, and across this resistance there will be an input voltage Vi. Now here we can say that Vi equal to 43.82 divided by 2K plus 43.82 into Vs, and it is equal to 0.956 into Vs. So Vi upon Vs is equal to 0.956. Now the voltage gain AV equal to V0 upon Vs can be written as V0 upon Vi into Vi upon Vs. This voltage gain V0 upon Vi just now we have calculated is, it is minus 1.5 into this Vi upon Vs is 0.956, and it becomes minus 1.43. So this is the final answer for voltage gain AV, and also we have asked to calculate Ri dash, which was 43.82 kilo ohms. So this is the final answer. Now next we'll see high frequency analysis of BJT. Now in BJTs there are two junctions, one between base and collector, one between base and emitter. We have already seen that if a diode is operated in forward bias, there is a capacitor across the diode called diffusion capacitance CD, and if a diode is operated in reverse bias, there is a capacitance across the diode called transition capacitance. These two junction capacitances will also present in this BJT. One capacitor will be there across between these two terminals, base and collector, and there will be one capacitance between base and emitter. These two capacitances between these two junctions have the capacitive reactance Xc equal to 1 upon 2 pi f into C. And if f is large for high frequencies, if f is large, then Xc is become very low. If X is low, then they create a path between these two terminals, means these terminals are shorted. These terminals are shorted, and if these terminals are shorted, the transistors cannot be used for amplification of high frequency signals. Now in high frequency analysis, we will take these two capacitances in consideration. Now when we draw the high frequency analysis of this BJT, in high frequency model, we will have to consider these the two junction capacitances which will be affecting the operation of transistor on high frequencies. The low frequency model fails to define the operation of a BJT at high frequencies, so a new model is formed which is called pi model, and it looks like this. This is the basic hybrid model, sorry, pi model for transistor operating at high frequency. In this model, this is the actual base terminal B, this is the emitter terminal E, and this is the collector terminal C. Between base terminal and the if base terminal B dash, there is a resistance RBB dash called base spreading resistance, is the resistance of base is the resistance of base region in the transistor. Base spreading resistance. Now in this model we have considered two capacitances C pi or CD and CD or CC or C mu. This CC or C mu is the capacitance between base and collector, and this capacitance is the capacitance between base and emitter. So both these capacitances we have taken into consideration. Now for this high frequency model, we can connect the other parameters like other components like RC, RL, RB, this source and source voltage and source resistance, as we have connected in the earlier case. Now from this model, we can have some equations. First, the transconductance GM, this one is given by magnitude of DC collector current upon thermal voltage Vt. The thermal voltage Vt is given by T upon 11,600, and it is nearly equal to 25 millivolt or 26 millivolts at T equal to 300 degrees Kelvin, means at room temperature. Now the next one is Rb dash E equal to R pi. This one, this resistance is equal to HFE upon Gm. The transconductance Gm and HFE we have seen in the earlier case. Number 3 is the relation between high frequency and low frequency parameters. HI is equal to RBB dash plus R pi, and it is nearly equal to R pi. So now if the parameters of this high frequency models are given, first we can calculate the current gain AI as minus HFE. Second, input impedance Ri equal to HIE, and it will be equal to R pi, and it will be HIE plus 1 plus HFE into RE equal to R pi plus 1 plus HFE into RE in case of unbypassed RE. This was the case of bypassed RE, and this will be the case of unbypassed RE. Number 3, voltage gain AV will be equal to AI into RL dash upon Ri. This equation will be used again. And last, number 4, our output impedance will be considered as infinite. Now, as we have discussed that this junction capacitances are affects the operation of transistor at high frequency. So now we'll draw the variation of current gain versus frequency. We know that the frequency, high frequency, the junction capacitances affect the operation of BJT. So at high frequencies, we will now see how the operation of BJT is affected, means current gain affected by these junction capacitances. At low frequencies, the current gain of BJT is sufficiently high, that is minus HFE, and as we increase the frequency, the current gain start decreasing, and we obtain a curve like this. The frequency at which current gain becomes 1 by root 2 times its maximum value, this is the maximum value, is called beta cutoff frequency is called beta cutoff frequency, and the frequency at which current gain reduces to 1 is called ft frequency, ft unity gain cutoff frequency. The beta cutoff frequency is mathematically given by f beta equal to 1 upon 2 pi rb dash e into c pi plus c mu, or equal to 1 upon 2 pi into r pi into cd plus cc. These two capacitors, cd is also called c pi, cc is also called c mu. And the frequency ft is given by hfe into f beta is equal to hfe upon 2 pi rb dash e into c pi plus c mu. We know that rb dash e equal to hfe upon gm. This equation can be written as hfe upon 2 pi into hfe upon gm into c pi plus c mu. This hfe will be cancelled out, equal to gm upon 2 pi into c pi plus c mu.